So, what are we on to today? Last time, we talked about some operations that we can do with graphs. And we talked about isomorphism and symmetry of graphs. And today, we're going to finish off graph theory with one last topic, which is paths and connectivity. So let's start by defining a path, which is basically what it sounds like, but let's go ahead and write it down. A path of, we'll also define length, a path of length n is a sequence of edges in our graph So let's say in the graph G is a sequence of edges, E1 through En. So the length, n, is the number of edges in our path. And a path is a sequence of edges that basically forms a path. One way of saying that, such that for I from 1 to n minus 1, the edges EI and EI plus 1, so each edge and the next, share an endpoint. So this is the definition of a path. It's a sequence of edges that match up end to end. And another definition, so for a simple graph, and let's remember, I'm giving this as an aside, but when we say graph, we generally mean a simple undirected graph. And we'll deal with directed graphs a little bit today as well, but we'll do that later. So for simple graphs, this is equivalent to, it's equivalent to consider the sequence of vertices V1 through, or V0 through Vn that the path goes through. And this is actually more often how we'll write it down. Just notice that in terms of the length of a path, the length is equal to the number of edges. The number of vertices is going to be one more. So we're going to start from 0 and list up to n, for example. And before we give some examples, a couple more types of paths that we want to consider, or a couple more pieces of terminology. A path is a circuit if, maybe let me use the notation that we used here. It's a circuit if the beginning vertex is the same as the ending vertex. So if it starts and ends at the same point, which is, hopefully what the name sounds like. A circuit means it forms a closed loop. A path is simple if, again, using the notation up here, all our EI are distinct, which is to say that it does not visit the same edge more than once. So in general, a path can go through a certain edge as many times as you like, but a simple path is restricted to going through every edge at most once. So let's see some examples. So let's draw ourselves a nice little graph. And let's label the vertices. Let's just give them some names. So this is A, B, C, D, E, F, and G. And so let's for example, A, B, C, D. So we're labeling it as in this definition with the vertices. But this is the path that is this edge, and then that edge, and then that edge. So this is a simple path because it only goes through each of these edges once. And it has length 3 because it traverses 3 edges and 4 vertices, which is going to be 1 more than the length. What's another example? So if we start from here, oh, I have mislabeled it. All right, I've labeled it differently from my notes. So my notes are going to stop making sense to me. So I'm going to have to just wing it. So if we do a path something like this, then that is going to be a circuit because it starts and ends at the same point. So how would we write that? That is G, F, this edge, then C, this edge, then B, this edge, then A, this edge, and then G again, this edge. So this is a simple circuit. It's simple because it traverses each of these edges once, and it is a circuit because it starts and ends at the same vertex. And what is the length? 1, 2, 3, 4, 5. Length 5. And so what is an example of something that is not simple? So if we take this edge, this edge, this edge, this edge, and then back to B, that is also a circuit. So we started at B, then C, then E, then D, then C, and then back to B, is a circuit. Not simple, because it traverses the edge between B and C twice, and it has length, I believe again, 5. It's 1, 2, 3, 4, 5. Since we traverse this edge twice, we count it twice. So this is a path of length 5. Very good. So this is what paths mean in undirected graphs. For directed graphs, we can make essentially the same definition. But of course, now that our edges have directions, our paths are required to follow the directions of the edges. So if we have some directed graph like this, call this A, B, C, D. Then, for example, ABC is a simple path of length 2. And it's a valid path because it goes from A to B in the direction of the edge, and from B to C in the direction of the edge. But for example, ABCD is not a valid path because this edge we have traversed in the opposite direction of the direction on the edge, and that is not allowed. So it's not a valid path because we traverse the edge from D to C backwards. Whereas for these pair of vertices, we could go either way because we have an edge in both directions. So there's no obstruction there. But if you only have one edge, you cannot go opposite the flow of the edge.